Alright guys, in today's video we're going to be looking at interpreting the graphs of these normal distributions. First off, let's talk a little bit about what a normal distribution is. A normal distribution, and you don't have to write these little key points down, I'll tell you what properties to write down. Normal distribution is a continuous probability distribution for a random variable x. It's actually the most important probability distribution in statistics that we're going to see. The graph of a normal distribution, we call it the normal curve. You may have also seen this thing called a bell curve frequently. Okay, so now here's the properties you do want to write down. In a normal distribution, the mean, median, and mode are all equal, and they're all sort of that highest point right in the center of the distribution. The normal curve is bell-shaped, as I mentioned earlier. It's a bell curve, and it's symmetric about the mean, meaning it's equal on both sides of the mean. It looks exactly the same. The total area under the normal curve is going to be equal to 1, and that sort of represents 100%. The normal curve approaches, but it never touches the x-axis, the farther away from the mean that we get. So it does look like it sort of stops, but it actually doesn't. It keeps going and gets closer and closer to the x-axis, but never touches it. Okay, so one standard deviation in either way is basically what this is saying. So if we take the mean minus a standard deviation or the mean plus a standard deviation, okay, the graph sort of changes direction. Okay, it starts curving from one direction to the other. That's what we call our inflection points. And those are going to be important to identify some things, as you're going to see later on in some examples that we look at. Okay. Now, probability density function, it's a discrete probability distribution that can be graphed with a histogram. For a continuous probability distribution, you can use the probability distribution function. Now, it has two requirements. The total area under the curve is equal to 1, just like we said about our normal curve. Okay, that 1 represents 100%. Okay, and the function can never be negative. It always stays above the x-axis. Okay, so let's look at mean and standard deviations. When we have a normal distribution, it can have any mean and any positive standard deviation. All right? So the mean sort of gives us the location of the line of symmetry. That's that middle point of the distribution. The standard deviation, on the other hand, tells us how spread out the data is. Okay, so let's look at these examples, A, B, and C. Now you're going to see if we look at these, notice A has a much higher standard deviation, and you can see how it's sort of more spread out, more flattened out. Okay? Then notice the difference in the means. Well, A and B both have the same mean, but they have different standard deviations. And you can see B, all the data is more compressed into that peak, and in A, the data is more spread out, more of a flat hill looking shape. On C, on the other hand, it's kind of about this, it's the same standard deviation as B, so they're both kind of the same steepness. But then our mean is now at 1.5 instead of 3.5, so sort of just shifted over. Okay, so let's look at an example. We got A and B here. Well, which curve is going to have the greater mean? Well, remember the mean lies in the middle of sort of that mountain, in the middle of that hill. It splits it right in half. So if we look at that, well then A is going to have the greater mean because we can see the center of A lies over 15, whereas the line of symmetry for B would be over x equals 12. Okay. Now, which one has the greater standard deviation? Well, remember, standard deviation means it's more spread out. So the one that looks more spread out, more flattened, is going to be B in this case. Okay. You see how it's more spread out than A. Okay, so let's look at a real-world example. We got these scale test scores from New York State, 4th grade mathematics test. Okay, and they're a normal distribution. You can see the curve there. Well, what's the mean test score? And then we want to estimate the standard deviation. Well, to find the mean test score, we're going to look to where it's symmetric. Well, right in the middle you're going to notice it sits right about 305 or so. Okay? Well, that's going to be our mean, right where we divide it in half. Then if we kind of go in each direction where it sort of starts to do that change in direction, you can see our 2 inflection points. Okay, so if we mark those 2 inflection points, and then we sort of measure out how far that is from the mean, each one is about 40 from the mean. So that means our standard deviation would be about 40 because those inflection points are 1 standard deviation away from the mean. If we go back to some stuff we learned last semester, those of you that weren't in here last semester, I know this is going to be new information to you, but don't worry too much about that. Okay, using the empirical rule, we know that 68% of the scores are going to be between those 2 inflection points. Okay. All right. So now let's look at something what we call the standard normal distribution. Okay. The standard normal distribution has a mean of 0 and a standard deviation of 1. Okay. It still has an area of 1 underneath the curve. Now, we can take any value and we can transform them into a z-score, which is what we call our standard normal score, by using this formula here. Z equals the value minus the mean divided by the standard deviation. Now, we're going to get more into using this formula later, but I just wanted to go ahead and show you that this is applied to our standard normal curve with a mean of 0 and then a standard deviation of 1. Okay. There's another picture of our standard normal distribution. All right, so now here's what you really need to write down. The standard normal distribution, as we get close to 0, or to negative 3.49 on our z-score, which is how many standard deviations away. So once we get a little, almost 3.5 standard deviations below our mean, the area starts getting close to 0. It's almost non-existent down there. Okay? As we go from left to right, the cumulative area, meaning the area underneath the curve, is going to increase. Now, if we look at z equals 0, which is our mean right in the middle, okay, the cumulative area there, which would mean the area to the left of 0, would be 0.5, okay? That would be 50% of the data. Now, if we get close to 3.49, that's going to be almost 100% of the data is to the left of that.